Okay, so yeah, this talk will focus, as already said in the introduction, on the GW method. And yeah, what will be the content? So first a bit, what type of spectroscopy are we looking at? And then also a bit touching on the questions that were now part of this Q&A. What are actually the limits of DFT-based methods? And then going a bit deeper in GW. And then also repeating a little bit what is the functionality that we have here. Okay, so what is this lecture about? So there will be a little bit of GW theory, so the basic idea and formalism. For more, I just point out there will be also more on GW theory and lectures than in the hands-on workshop in November in Shanghai. And the other thing I want to also focus rather on this talk are a little bit the practicalities of GW, so how to obtain well-converged GW results. And I also want to say it again, there's an overview in sections 4.2 to 4.4 in the roadmap, right? So I have a lot of references also in this talk, but if you want to look them up again, so this is certainly also a good reference for that. Okay. So what is theoretical photoemission spectroscopy? And I just want to clarify again, what is actually the types of spectroscopy that I want to discuss here. So it's for, so it's photoemission spectroscopy, inverse photoemission spectroscopy, and what I just want to touch at, so actually not really explain, that would be absorption spectroscopy. So in photoemission spectroscopy, we irradiate our sample with light with a certain frequency nu, and in this process, an electron from a formerly occupied state is removed from the sample, so it's promoted above the vacuum level, which is here indicated by the dashed line. We can also have the inverse process where we have an electron with a certain kinetic energy, and this undergoes then an irradiative transition to an unoccupied state, and thereby emitting light, also with the energy here, h times nu. We call this charge excitation because here the system is then charged positively and here negatively afterwards. So this is the type of spectroscopy we can describe with GW. So the other case, when we have the absorption process, so when like an electron is promoted from an occupied state to an unoccupied one, so we form here an exciton, so a bound electron hole pair. So this is not the type that we can describe with GW, but for that we have to go beyond GW and solve the beta equation BSE on top, or as an alternative approach, use time-dependent DFT. Just to make the distinction clear, so GW can only describe these processes, photoemission and inverse photoemission, so charged excitations. To go a little bit more in detail in the photoemission spectroscopy, we can get the ionization potential, IP, for a certain state S. It could be, for example, the HOMO of the molecule, by measuring the kinetic energy of the ejected electron. We know the frequency of the light that we were using, or that we kind of like were shining on the material or the molecule. For a molecule, the reference is the vacuum level. So if you just take the difference between these two terms, we would have already the ionization potential. For materials, the reference is the Fermi level, so we also have to subtract the work function. So that's the definition of that's how we get the ionization potential. So the ionization potential is then the negative of the electron removal energies. So how are they defined? So this is here the total energy of the ground state with n electron, and this energy here denotes the energy of the system with n-1. So I have an electron removed from the state S, and the difference between these energies is then the electron removal energies. This defines the electron removal amplitudes. So we will look into them later, just also to have them here on the slide. What is ncat? So that's the many-body ground state. And this is the annihilation operator that removes an electron from that many-body ground state. So you can write this down in a similar fashion, in an analogous fashion for the electron affinities. So for like the inverse process, inverse photoemission, I refer you here to this this review. If you also want to have a look at this, so in the interest of time, I will go on here to show some examples that say, how does it look like, such a photoemission experiment in the case of molecules? We have here pyridine. In black, we have the experiment. You see here at around 9.5, the first peak, and I tried to indicate this. This is from the electron binding energies, basically, of the HOMO and HOMO -1. Here indicated with like the blue and red line. And the next peak basically belongs to the HOMO -2. I calculated here the discrete quasi-particle energies, broadened them to basically get a better resemblance to experiment. So that's what you can basically compute. So such ionization spectra. You can also then compute the electron affinities, get fundamental HOMO-LUMO gaps as the difference between the ionization potential of the HOMO and the electron affinity, which are important parameters, for example, for organic semiconductor molecules, etc. Much more common, honestly, for photoemission spectroscopy is so-called angle-resolved photoemission spectroscopy, ARPAS. So for a material, the spectra are angle-dependent with respect to the crystallographic axis of the material. So these are here indicated by A. This direction dependence is indicated by a wave vector K. So with a certain angle configuration, you would, for example, get such a spectrum. Now we can vary the angle and get different spectra, and this is basically shown here. So there's basically many spectra with different K vectors stacked behind each other. So each of these different lines is basically recorded at a different angle. Well, this is usually not how you notice this figure. So usually we plot along like a certain angle dependence, or then a certain special points in the Brillouin zone, which gives this probably more familiar plot of band structures. Shown here is for zinc oxide, only here the occupied states, basically converting this figure into this representation. We have the experiment here in white and purple, and the computed bands are basically these red ones from GW. So what you get from these experiments are band gaps, band structures, density of states, band parameters like band velocity, lifetimes, etc. So far to the experiment, and the question is, what could we do with DFT, and what are the limitations? So the easiest idea would be to just use cone-charm DFT eigenvalues and then relate the negative of these cone-charm eigenvalues simply to the ionization potentials for a certain level n. I have here an example for the benzene molecule computed here with the PBE0 functional, so already a hybrid. You see that the difference on average for these first valence states is 2.2. It's already quite high, so it's usually around 2 to 3 eV. It gets like larger in absolute values if you go to deeper states. So for deep core states, it's already around like 30 eV for like the second row elements. We get 2 small gaps, and already here an indication that with GW we get much closer to experiment. Now for the solids, it's very similar. We have here the silicon band structure computed, basically here the DFT eigenvalues with an LDA functional. We have here the experimental gap of indicated with this green dashed line. You see it's much too small. If you take the eigenvalues from Haag to Fock, you see that you drastically overestimate the band gap. And again here, much better with GW. To give a bit more statistics, we have here band gaps from different semiconductors and insulators. We have the theoretical values on the left, and on the x-axis the experimental one. So the perfect agreement would be if they all are on the blue dashed line. We are pretty off with PBE, while with here these different GW flavors, which I will explain a bit more later, we are pretty much on these blue dashed lines, so a very good agreement. A better method than using eigenvalues was already mentioned now before, and there were a lot of questions. So I hope some questions are a bit even more answered in detail with this slide. So it's the delta self-consistent field method. So you won't get easily like the deeper valence states, right? So the other parts of the band structures, but it could be an approach to get better band gaps, for example, or ionization potentials for the HOMO4 molecule, or electron affinities also for the molecule, then DFT eigenvalues. So what's the idea? So you perform 2 calculations, as already mentioned. One to get the total energy for the ground state with n electrons, a second one where you moved an electron, for example, from a 1s state, or also from the HOMO, and calculate the difference. To get that one for the electron affinities is similar. But here for the second calculation, we basically add an electron to the system. So that's the n+1 system. Calculating the difference gives us the electron affinity. So that works actually very well for small molecules. If you go to larger conjugated structures, you already see it's much more difficult to often constrain like the hole, even if it's a core electron, so it gets more difficult. I don't say impossible. And also the accuracy then deteriorates. Generally, for periodic systems, we have the problem that periodic binary conditions and n-1 calculation are obviously a problem. So you have to keep a charge neutral supercell, and you achieve that either by adding a background charge or by artificially adding an electron to the system, which creates artificial exciton binding energies in the system or different artifacts simply. So it's possible, but potentially inaccurate. And another point is you can have many body effects in your spectra. So not only having the main peak here, but for example, also a satellite. Okay, so now let's go to GW. And I just can cover like the theory very briefly here. I want to refer you here to this review article, which we wrote in 2019 together with my supervisor at this time, Patrick Rinke, and also my colleague, Mark Dvorak. We try to focus there also on the practical aspects, numerical techniques, etc. And to show this equation again, how are the electron removal energy defined? So basically, as energy, total energy of the n electron system minus the energy of the system where one electron has been removed from state S. Similar for the electron addition energies, but here we have like the system where we added an electron in state S. Now we have like also these electron, like these transition amplitudes defined in terms of like these annihilation operators, which kind of removes an electron from the system, or for the addition process that adds an electron to the system and acts here on the many-body ground state, NCAT. So central to GW is the Green's function, as said before. So it's a propagator, and you see if I write down this propagator in this form, you can actually see the process basically directly happening. Let me explain a bit. We have like this is a spatial coordinate, x, y, z. We have a second one, r prime, and then also 2 times t and t prime, and sigma is here simply the spin. So you can see what this propagator is basically doing. So we have here the time ordering operator, and what it is doing is that it simply puts the earlier time to the left. So if p prime is earlier than t, this operator will go first and act first on the ground state. So what is this doing? So we have here the creation operator. So basically it creates an additional electron. So that's the electron inverse photoemission process. It propagates through the system, is later annihilated at time t at the spatial point r. So if the times are reversed, you see it also allows for the second process. Then the time ordering operator puts the annihilation operator first, and then we basically first delete the electron. So this is, I think, shows very clearly that we define basically directly this process by defining the single particle Green's function like this. And to now make contact to experiment, we make a Fourier transform and go from the time domain to the frequency domain. Let's have a closer look here. So this is the Heaviside step function, which becomes 0 for negative arguments. So basically, this is the electron removal branch. And this term will get 0. So basically, meaning if I want to compute like the energy, removal energy of the occupied state, so we have only this term. If I have the one for an unoccupied one, we have only that term. So in this way, also the time ordering is kept in some sense, or is directly kept. So now interesting, what you can see here, let's look at the denominator. Let's say like this. So we have here eta, which is a small infinitesimal. And you see that the poles of this function correspond to these excitation energies epsilon s. So that means if omega equals epsilon s, we divide by 0. So that's a pole, a so-called singularity. And so we directly have the excitation energies defined in the method, which is not the case basically in DFT, just as a hint. So now, when we apply now the so-called Kramers-Kronig relationship, we know when we have a pole in the real part of the quantity, and our quantity here is G, we have like a peak in the imaginary part. And if we want to calculate rather a spectrum, it makes sense to take now the imaginary part of G because of Kramers-Kronig, right? So if I have a pole in G, I have like a peak in the real part, I have like a peak in the imaginary part. And this spectral function is basically the one that we could directly connect to experiment, so the photocurrent that you actually measure in a photo emission experiment. So now let's have the next look. So if we would have like non-interacting electrons, that would mean I would act, for example, with the annihilation operator on a single determinant, because our ground state is defined by a single Slater determinant, meaning that if I remove an electron from state S, I create exactly one excited state, exactly one excited state Slater determinant, meaning I get simply here a sharp peak, nothing else. However, if I go to interacting systems, I have not my ground state is not described by a single Slater determinant, but by many. So I have a reference determinant, then adding all like the singly occupied, doubly occupied, triply occupied determinants, and our annihilation operator, for example, is acting on all of them, giving in the end like a bunch of, let's say, electron removal energies, basically the contributions from all the different determinants, which is basically shown here. And when those merge together in one broad peak, then this is what we call the quasi-particle. This peak has like a certain width, so it's also connected with a certain lifetime. So now I was coming with the definition of the quasi-particle peak rather through an explanation that maybe makes sense to people that are very familiar with full CI. I'm also trying to do a more intuitive explanation shown here on this picture. Let's say, imagine you have like an electron ejected during the process, then the other electrons come and rush to screen like the bare hole. And then this composite object of electron, which is interacting with its polarization cloud, the electron is basically moving through the system. Doesn't need always to be like the same electrons around it, but from far it looks like a hole together with like its polarization cloud is traveling basically through the medium. And that's this whole composite object. This is the quasi-particle, which has properties such as dispersion, lifetime, a weight, a satellite spectra, etc. So what's now the basic idea of GW? So an analogy to DFT, we replace the exchange correlation potential by a self-energy, and the self-energy is the energy the quasi-particle feels due to its own presence. A little bit hand-wavy, but I think that's the best we can do in this time. So G stands here for the Green's function, and W for the screen-Coulomb interaction. So it's not a name of a person, but rather it's basically the matrix notation we typically use for these properties. The most common flavor is a so-called single shot G0 W0. How it works is that I take my Kohn-Sham energies for state S, and then at the correction term, which contains this self-energy. And this is what we call quasi-particle equation. So exactly this expression is the one. Okay, and to explain the procedure in short, so we first run a DFT calculation to get our Kohn-Sham orbitals, epsilon ks, and the corresponding orbitals phi ks. From those, we build G0 and W0. We calculate then the self-energy from G0 and W0, and then solve this equation. So let's have a bit closer look. As I said, first the Kohn-Sham DFT calculation. Then we calculate the Green's function, where we have like the orbitals in the nominator, and here the energies enter the denominator. We then construct from G0 the polarizability as product of basically two G0s. Then we compute a dielectric function, and what enters here is this chi0 together with the bare Coulomb interaction. So bare Coulomb interaction is 1 over r minus r prime. And once we have the dielectric function, we can get the screen Coulomb interaction by multiplying its inverse with the bare Coulomb interaction and then taking the integral. Okay, so we can then construct the GW self-energy as I have written before by solving this frequency integrals over G0 and W0. So this would be the full quasi-particle equation. What I had on the previous slide was already an approximation. So this would be our quasi-particle wave functions. We make now the approximation that we insert instead the Cohn-Charm orbitals, and then basically integrate also from the left and then get this following expression. So we usually separate the self-energy in the correlation part and the exchange part, and then subtract the exchange correlation functional from DFT. As you can see, the right-hand side already depends on the solution, on the GW energies, on the quasi-particle energies. That means we have to solve it iteratively. We can start here with a guess, for example, the Cohn-Charm DFT energies, and then get the solution, update, insert again, etc., until we solve this fixed point equation. So this is the standard approach, doing this iteration of the quasi-particle equation. You can also do a so-called linearization of this approach. A set-shot approach is, by the way, also implemented in AIMS, but I would not recommend it. Other ways to get a quasi-particle solution is graphically, or to calculate the complete spectral function. And this is sometimes necessary to understand if you got a unique solution. So that's why I want to mention it. For the graphical solution, what's the procedure? So you calculate the self-energy matrix element for a certain state S on a fine grid, frequency grid. You typically plot like the real part of the self-energy. This is shown here for the HOMO of a water molecule, plotted in the range from -30 to 0 eV. You see have a quantity with a lot of structure. So these are actually poles, so like where you basically have a divide somewhere by 0 in sigma, so it's a singularity. I just broadened it so that you can see something in this plot. And then you try to find the intersection with like this straight line here. And this is plotted in red, and you see the intersection here. The first one is this dashed line. So now you see have also other ones over here. What's to consider is the spectral weight, and you see that we take here the derivative and then the inverse of it, meaning if the Z value is large, then you have a lot of spectral weight. And this is basically here the main solution. We are like the line is flat, so the Z value will be very large. So the larger the better, or is will then close to 1, and this will give like a very small value for Z. So this has low spectral weight. This is rather corresponding to a satellite feature. So sometimes it's necessary to look into this to see if you have a unique solution. So now the most accurate way to get actually the solution is to calculate the full spectral function, which is really expensive typically. You see here that you include also the imaginary part of the self-energy and not only the real part. And as you can see here before, I talked a bit about the spectral weight. So it's maybe not so obvious. If you have looked at self-energies before, you directly see it. But if you plot the spectral function, it becomes very obvious. So here at around minus 12 eV, as shown here, we have indeed our main peak. We have a very sharp peak, which carries clearly the largest spectral weight. And then we had like intersection a bit further. So you see this is very small spectral weight. These are what we would call a satellite in the method. Okay, so an important point is not only how to solve it, but also the frequency integration, as James already mentioned. So how to solve this frequency integral. And the issue is that both quantities G and W have poles, so we can't do a straightforward numerical integration here. However, there are a bunch of tricks, and what we implemented in AIMS is the analytic continuation, which I abbreviate as AC, which is suitable for valence states and gaps, has an n to the power of 4 scaling. The contour deformation is more accurate, suitable basically for all states, including deep core states, scales n4 for valence states, n5 for core levels. Much more accurate, but also much more expensive. Let me quickly explain what's the idea behind it. So The idea is that the self-energy has a smoother structure for imaginary frequencies compared to real ones. You see here for the real ones has a lot of structure. And the idea is to have a set of reference frequencies, let's say 200 imaginary frequencies, calculate the self-energy for each of this frequency, and then basically perform a fit to some analytic model which has poles. For example, the two-pole model, we don't know these coefficients A and B, so we basically get them by fitting to this reference values. And then there's basically a theorem that says if you know the quantity on the imaginary axis, you also know it on the real one. So you basically then for real frequencies use the same coefficients and just insert your real frequency. You can have more elaborate models, for example, the Pade model, which has more parameters, A and B here. And then it's also more accurate. As you can see here, we have this is for benzene, the self-energy. The solution here are roughly at 9 point something EV. The exact solution in blue is contour deformation, and we have the Pade model in green. You see it captures some of the poles here, some of the pole features, averages nicely to the more straighter part of the self-energy. It doesn't capture everything, okay. But the two-pole model, you see it fails to capture these poles also here, but it manages, at least in this case, to somehow average through the self-energy structure. And for more details, please read this paper. So the contour deformation, the idea is to now move the problem to the complex plane. We define the contour integral in this very specific way. So in this is the green shape is the contour integral. Basically, this part has four parts, the one along the real frequency axis, along the imaginary frequency axis, so this term, and then two parts going here around these arcs. You can show that these two terms get zero. And we want to have like this term, right? The self-energy along the real frequency axis. So we simply have to subtract the imaginary term here from the path integral. You can read more about the implementation, for example, in this paper. So that was the frequency integration. It's an important point in GW. Next one is basis set convergence. It's usually slow as for all correlated methods, be it MP2, RPA, cup cluster, etc. I show this here again for the benzene molecule, for the HOMO level. I plotted basically this HOMO ionization potential dependent on the number of basis function or inverse of the number of basis functions. So we have here Gaussian basis sets from triple zeta quality, so quite small, to 6-tuple quality. And you see that even for the largest basis sets, we are not quite there. So we have to extrapolate. And please note, for the smaller basis sets, you might be still like 0.3 to 0.4 EV from the actual results. Now with FHI-aims, we have also for certain use cases also the possibility to, or for solids in general, to use different combinations, for example, using a tier 2 NaO as basis and then add very specific functions on top to accelerate such convergences. Next point, the starting point dependence is very pronounced in G0W, not shown here for the water molecule and the HOMO energy. So we usually underestimate the ionization potential with an underlying PBE functional. With Hartree-Fock, we would overestimate. So there's a sweet point usually when you use a functional with 20 to 30% of exact exchange. Then you basically is a experience closest to experiment for molecules, right? So this is for molecules shown here. To reduce the starting point dependence, there are different self-consistent schemes in FHI-aims. So the purest approach is fully self-consistent GW sketched here. So you really iterate, you basically solve the Dyson equation as shown here, starting with a guess for G is usually G0, and then calculate chi W and sigma the full way. So this is very expensive. It's only feasible for small molecules, maybe 10 or maximum, maybe 20 atoms. The approximations to the self-consistency, you can only iterate eigenvalues in G. So if you remember, there's, for example, in G, in the denominator, we have the Concham eigenvalues. You could then replace them by your quasi-particle energies and do this over and over again until you achieve convergence. That would be EVGW not. You can also iterate the eigenvalues in W. So that was not on the slides, but if you look then in the implementation, you see that they also occur there. So you could also replace the eigenvalues in W. Is my personal opinion. I would not recommend it because this often leads to to under screening. For the fully self-consistent GW, so this is in this paper, by the way. Okay. Now, finally, I want to close with a few practical guidelines. The points that you should consider when running GW is what frequency integration technique to choose, your basis set choice, convergence, the starting point dependence, or the choice of a partially self-consistent scheme. And there are also other convergence parameters, for example, the number of frequency points you use to, for example, in the Pade model, right, as a reference frequencies, etc., and how many Pade parameters you choose. So going to molecular valence states, generally analytic continuation works well enough. So I would use a Pade model if it's numerically stable and if it's available. You have to check convergence with respect to the number of Pade parameters. Usually there's a guideline of 16 is usually good, but also with respect to the frequency points. PB0 is usually good for molecules, right? So I say explicitly for molecules, but you might also try a self-consistent scheme, is typically affordable. So you can, for extrapolation, you can use a Dunning basis set, but this is just one, right? So you can also use different one like NAO optimized ones. For molecular core states, contour deformation should be used, as I said earlier. So deep core states here with binding energies larger than 100 eV. You should definitely use some self-consistency in G to get a unique solution. So that's actually very important. All the schemes listed here work well. So this, what I call heading shift, is an approximation to EVGW naught, basically stopping at the first iteration step of EVGW naught if you want. Compared to experiment here in the table for the core 65 benchmark set, they perform all very similarly for absolute binding energies of 1s states. You need relativistic corrections, of course, and you also need either a basis set extrapolation or, as I said, sometimes we can also design very specific basis sets to accelerate the convergence. We found that practically also tier 2 and then adding Slater type functions, so STOs, works also pretty well. Now for the periodic solids, it's the same story. So you have to check how many frequency points you use. Auxiliary basis set is also here an important point, convergence with K points anyway. And also basis set, of course. So here an extrapolation with correlation consistent Gaussians wouldn't be feasible or also not in any case practical. So what we do here is usually using also a tier 2 NAO as basis and then at STOs. This is zirconium dioxide, and you see also here, if you progressively add more STOs, how you then basically start to converge the calculation. And as already mentioned, this is the implementation paper here from 2021. To summarize quickly the functionality, so we have single shot G0 W naught for molecular valence states, molecular core states, periodic systems, eigenvalue self-consistency, for all the molecular cases, fully self-consistency also only for the molecular cases, but it's also terribly expensive. I think is not really feasible. Just to mention it briefly, even though that was not part of the talk, we have there's also BSE performed on top of GW, possible for molecular core and valence states, and also periodic systems now. Vertex corrections, a bunch, cumulants. This is basically related to getting correct satellites. And other ones that are more sophisticated ones. But again, this is typically also expensive, at least the other two ones, and molecules only at this point. And I want to close now with a list of the literature summary. So I didn't put everything, I just picked what I consider the most important implementation paper for each of or first benchmark of the method, all of these flavors of GW implemented in AIMS. And then I know it's not today, but happy computing tomorrow. And now I'm looking forward to your questions.
Thank you, Dorothea, for the nice presentation and all the overview of what is implemented within FHI-aims. And as before, the Q&A session is again open. You can use the Q&A button to ask your questions, or also on YouTube Q-Share, or feel free to raise your hand to speak. And we already have a first question from Samuel Ponce. Many thanks for the presentation. On slide 26, could you elaborate on the O(5) scaling of contour deformation for the core states?
Yes, it's not directly visible from from the slides, so I didn't put that much technical details up, but I can nevertheless try to explain quickly. 25, right? So if you have the contour deformation, maybe this is better on this slide, you will see that that this term scales n to the 4, so that's the integral along the imaginary frequency axis. But this term is basically obtained by applying the residue theorem. So meaning that you end up with like a sum over occupied states, basically then times occupation factors times W, where the argument is epsilon minus omega, times the Heaviside step function. And then you will see that for core levels, you will sum over the whole occupied states. And then W scales n to the power of 4. You have like a sum over occupied states in front of it, and then suddenly you have your n5. I mean, I would have to write down exactly the equations, but it's basically this term that is screwing you over, like which comes from this path integral. And to explain, like for valence states, you have only very few residues, right? So you have to then you keep basically the W scaling, because you don't sum over all occupied states, but only 1, 2, or 3 contributions.
Thank you, Dorothea. Thank you, Samuel, for the question. Any additional questions? Maybe just a quick question for me. Could you comment on the limitations of the different approaches with respect to system size? So what's currently possible for example, the periodic GW part and also the molecular ones, maybe the biggest test cases you already ran?
Well, with the M4, this one for the molecular case, yeah, I think like 250 is okay. So I mean, need a couple of cores. And I think as James had a figure on this in his slides where he had like 80 zirconium or 81. Yeah, it's around that. I don't know how much exactly. I think it was something between 80 and 90 in the system there for periodic systems. But I think that was then 20,000 cores, right? And yeah, fully self-consistent GW, I would say that's rather maybe 10 to 20 atoms really feasible to take there. The eigenvalue of self-consistency is typically not adding too much. It's more like, yeah, you run maybe a factor 10 or something more, right? And yeah, I mean, the BSE it depends a bit what you do, right? So for molecules, typically GW is the more expensive step. And the BSE is then faster. For periodic system, I would not, yeah, might be more, depending how big your K grid then is, right, for the BSE step. That I can't clearly say. But for the vertex corrections, the cumulant is not costing much on top. So there's a miracle of the cumulant, but also are very expensive, right? So then it's more like a few, I don't know, 10 atoms, 20 atoms with like these vertex corrections.
Thank you, Dorothea. There's another question about the convergence with respect to the imaginary frequency points when using the analytical continuation. Usually, how many points do you need to be converged, and which kind of grids can be used within FHI-aims?
So grids, the standard is the modified Gauss-Legendre grid. And so it depends if you really want benchmark quality. I would say like 100 grid points is a very safe setting. So you probably can try even less, like maybe 60. But I would say 100 is very safe. It's a good setting. I mean, if you really want to run a benchmark of small molecules, you can also use 200. It depends also a little bit on, let's say, typically if you use a pattern model with 16 parameters, you definitely have to, I mean, you have use at least 16 frequency if your pattern model has like 16 parameters, right? So, but it's better to use more because you also have to, there's they enter in the second part where you do a numerical integral in the technical implementation. So I would generally say, please use more than 16 frequency parameters. But let's say if you have 128 particle parameters, you need at least 128 frequencies, right? So it's also a question, if you see you have to, your self-energy has a lot of structure and you need to use 128 parameters, then also you have to use 200 frequency points. But general is 16 parameters, 100 frequency points is usually really safe.
All right, thank you. I hope that answers the question. Then there's another question. Is self-consistent GW usually accurate with in combination with BSE for neutral excitations, or does it depend on the type of system or whether it's a periodic or molecular system? What is the general guideline in choosing GW flavors with different types of molecules?
I think there were several questions at once.
Yeah, I think there are probably two different ones, but yeah. So the first one is self-consistent GW. Is it accurate with BSE for neutral excitations, or does it depend on the type of molecular system?
I think for fully self-consistent GW is not implemented in together with BSE, with neutral excitation. So you only get like charge neutral excitations from it, right? So only the photo emission experiment, and it's also not implemented in combination with BSE, as far as I know. Because the output is a bit different. You don't get like, with the other ones, you really solve like the quasi-particle equation and get discrete quasi-particle energies. When you run fully self-consistent GW, you get like a whole spectrum, right? So you really plot the spectral function. And as far as I know, it's not implemented. So you would have to go there and identify where are the peaks to then provide an input for BSE. And as far as I know, is not done. And I think also not very reasonable, I would say. The second question, which GW flavor to choose? So for core states, I would definitely go for something like EV, GW0, or an approximation of it, like the heading shift. So that's necessary. Otherwise, you won't get the solution. So not like a bad solution, but no solution at all, because the separation between your main excitation and the satellites is not right. So you have a major charge transfer and a really crazy multi-solution behavior. So you definitely need this to make the theory right. So that's a very strong point. Otherwise, for valence states, but depends a bit on the system. So as I say, like G0W not at some hybrid functional like PBE0 is already in most cases good, and otherwise I would rather use I would always rather use EVGW not. So I would usually go for this scheme, because according to my opinion, it works for the right reason, right? So here you changed arbitrarily somehow your screening, and this is usually not good. So like you go into the tendency to underscreen. But this is other people will tell you differently. So I would always rather go for this scheme, because what is doing something that is basically separating quasi-particles from satellites, and it's doing something in the theory that I understand, and here seems to be arbitrary to increase the screening. But a lot of people like that. And tune the starting point underneath. Okay, so I would either tune the starting point or use one of the self-consistency schemes. So my proposal is use EVGW not at a PBE functional, usually works well, or use G0W not at PBE0.
All right, thank you, Dorothea. I hope that answers the question. There's another one, and it's on why are the Dunning basis sets typically not recommended for periodic systems?
So, I mean, yeah, the Gaussian basis sets are basically really large. So you get in ill conditioning already in your S-step very quickly. That's an issue, right? So if there's Gaussian codes that do, of course, periodic systems like CB2K, but then they have special short range functions so that you don't get into the ill conditioning. But these basis sets are for molecules. So yeah, you would have really not a good chance with bigger molecules even to get through with it. I mean, maybe bigger molecules still, but like solids, definitely not, I would say. Yeah.
Yes, thank you. Then there's another question from Samuel, and could you comment on the validation efforts between GW for periodic solids and FHI-aims and other codes, so for example, Yambo, Abinit, Berkeley GW, and so on, and the stability of the analytical continuation in general? So what is the order of magnitude between the agreements between these different codes? Yeah. Yeah, I'm smiling a bit how to say this. So there was efforts in that paper, which I actually didn't want to mention too much, but this is another story. So it was a comparison between Abinit exciting
GPOR, and AIMS. These 4 codes where we tested a bunch of solids. And there's a comprehensive benchmarks for molecule, right? The GW100, and a lot of codes put effort and achieved really good results, really pushing it, even different basis sets going in an increment around 50 millieV. So for solids, it was much more difficult, right? So because there's so many different flavors then implemented in the codes, and there was not so much effort yet to make the codes numerically agree. And I think this is still missing in the GW community, to put there more effort to get the same answer with all the codes. But then it's partly it's not even that's not implemented, but rather that converging such things out with really tightly out with the basis sets, that's tricky. That's computationally expensive, and then other codes might not reach the convergence there. So that was our main problem, and then we had to use extrapolation equations and right. So such a numerical benchmark, one should afford to really converge out brute force. And if we then say, okay, for some systems we had deviations of 100 millieV or even 200 millieV, that's not very satisfying. But I think it was mostly due to the fact that other codes, the implementation, were not able to converge out. So also the conversion is not the same for all systems. Silicon behaves very nicely. You can converge it out very easily, and all codes get the same answer. There was no problem, right? So you have more complicated systems like zinc oxide, and then the codes disagree by 0.2 EV. So it's an issue the whole community has to work on, and this is more like an issue of like computational efficiency, as I think it should converge out K-grids to converge out basis sets in particular. And there was another question before, analytic continuation.
Yes, so, exactly.
So yeah, two-pole is usually more stable. So that won't give you arbitrary results whatsoever. But as you see, it's also right, it's a two-pole model, as already the name says. So the Pater model is numerically less stable because it's in the end like a Thiele approximant. You can also say, you see if you can rewrite this, and you see it's like a recursive procedure to get the coefficients, and that makes it numerically a bit unstable. So it's usually my experience for valence state numerically stable enough. So valence states may be up to going from 0 to minus 20 EV. And then it starts to get numerically, how to say, you will run a second time with a different number, of course, and your values start to fluctuate in 10 to the power of minus 3. The deeper you go, the worse it basically gets. But that's why I'm saying for valence states, it's usually fine. Then I would use Pater if available. Two-pole, as you see here, is not bad, right? So it still averages through it. It's more like if your pole is too close by, then it could happen that you're deviating more. And contour deformation is really stable, so there's no issue at all.